Okay, yeah. So I'll cast your guys' computers here. Yeah, I think so. Let's see. So this one's a little bit like worksheet one, other than it's not that it'd be really clear to you, but I did discuss it. It's in metric, so um, let me stop casting again real quick. Yeah, I'm on worksheet three here, so I'll jump out for a minute while Kennedy gets in. Yeah, worksheet three. That's what I have going in. It's the one that I have up. I did post the video from last Monday when I started worksheet two, one and two. But yeah, worksheet three and four is the last two we need to cover. That's what I have pulled up here. And the appendix to go with it. I think for worksheet one, we actually technically didn't need the appendix. It wasn't until worksheet two that we needed the appendix. But then I think we do need it for this one though, just for just for the last couple, the fit and the IT grade maybe. Okay, cool. So here I am. I'll send my screen back to you guys and I'll jump in. Okay, so worksheet three, here it is. Metric, yes. So I'm in. So first I'll just go over the example A that was already given here. Um, we're looking at A column for this problem, the shafts and the hole. Yeah. So all I had to do was actually fill out for the limits itself. All I had to do was fill out the information given. So for the hole, we have 6 to 6.03. And then for the shaft, we just take the dimensions they gave us, 597, 594. And then the basic size of that, I think I've said would be definitely the bottom row, at least to D. And then if we were to do problems E through H, that would probably be top row is my basic size. The one that just looks like the most normal number and doesn't look like it's all tolerance weird. So that's 6 is the basic size for A's example. And then the tolerance of that would just be subtracting, should be subtracting the difference between the two, like we would. The amount of a specific dimension is permitted to vary. So 3 minus 6 was a 0.03 for the hole. And for the shaft, it's the same. If we 597 minus 594 is actually ends up being the same tolerance, 0.03 of allowed variation. So then it just wants to know what's the upper deviation. This is the difference between the basic size and the permitted maximum size of the part. So for the shaft, it ends up being 0.03 again. It's 6 minus 6.03. It's funny they have it listed as a negative here, and we don't have it listed as a negative here, which I look at that as a positive value anyway. It's a larger size than the basic size. So it's interesting that we've got a negative sign down here. I would ignore that as far as. And then when we go to the shaft, we're subtracting the basic size from the largest shaft size, 597. We end up with the 0.3 again. So this chart has a bunch of 0.03 values here. So then the lower deviation, it says what is the difference between the basic size and the permitted minimum size of the part. So that's a 6 minus 6, so we're just 0 for our lower deviation. And then this one here, we're actually subtracting this from 6, right? So the basic size minus the smallest shaft size that's allowed, and that's actually 0.06. These are millimeters, by the way, too, of variation. So if I say inches, I'm wrong. And then we have the one that's a bit of an outlier. I always forget this. What this fundamental deviation concept is that it's the closest deviation to the basic size. So if I look at my two deviations from on the whole, I have a 0.3 and a 0. So I picked the one that's for the fundamental deviation. I just picked the one that's closest to the basic size. So 0 is closest to 6. Essentially, it doesn't vary from 6 at all. So the lower deviation here, so it's 0. Yeah, 0 is the fundamental deviation. On the other side, though, we have the lower deviation. Let me see this. Yeah, the small shaft size. Where are we at? Oh, the one that's closest to the basic size. So it's not the it's so it's what I say. I guess it's not the lowest. It's not the lower deviation here. Actually, the upper deviation is closest to basic size. So point. Say again. Closest to the basic size. Yeah. It's still the one that's closest to the basic size. It just happens to be the upper deviation this time, not the lower deviation. The one that was closest to basic size for whole was the lower deviation. The one that's closest to basic size for the shaft is actually the upper deviation right here. Sorry. That's all we're looking for. And that's one that I don't remember that. So every time probably every year I pull this up, I'll forget what fundamental deviation is. But I mean I understand maybe the concept now every time I look at it. But I get upper and lower deviations. Those come quite good to my mind. But if you were to ask me on the street, hey, remember what fundamental deviation is? I'd be like, no. What is it? Closest to basic size. Okay. The rest we don't have here. So really, yeah, the rest we don't have here. This is filled out now, but where they found this is where is maybe a little bit mysterious, but I can't remember what this says. It doesn't really give a real clear what I found was when people were asking me, this isn't really clear on where I'd find this information. It's like an IT grade, and then it has this big old paragraph about what an IT grade is, blah blah blah. This would be nice to have put first, since it's what I need to do. Find your fit first should be before I look for the IT grade. Um, so what I'm gonna do is find my fit first, and they determine this fit, and how they determine that that was the fit for here is I'll show you. I'll show you. So we would have had nothing filled out here. I should flip these two rows and look for your fit first, and then the IT grade will come naturally if it because it's based off the fit. So how we find fit is I'm going to go over my appendix, and I'm going to go down past the inch charts and into the well, if my appendix is going to have those. Oh, see, sometimes mine doesn't load right, but I'm looking for the metric. I think it's going to be here. I'm looking for the metric charts, which start on slide 8 for the or of this PDF, or A.2. Everything above that is all inches. So here we are into metric limits and fits, and we haven't used these charts yet. So I think from here, there's only a few. I think there's a blank page at the end. So there's this one, which is what they classify as whole basis clearance fits. The charting looks a little bit different. It says dimensions are in millimeters. So now I'm actually looking at millimeters. I don't think I'm looking at thousandths of a millimeter. I think otherwise it would tell me, hey, these are in, hundredths or something of a millimeter, tenths of a millimeter. They're not. I think these are just whole millimeters. And so it's a little bit different chart. And then let's go this. I think this one's kind of stays with that same method though. These are just millimeters I'm looking at on this chart out to 3 decimal places. So I've got a whole basis transition and interference fits, slide 2. And then I think I've got some like shaft basis clearance fits, yes, and maybe another one that's shaft basis transition and interference fits. And I think that's the last slide. So there's like 4 metric charts here towards the end, starting on slide 8. But what we're going to look for here is similar to how we did use the other charts for inches, is that I'm going to look for the basic size that I'm working with. So I'm looking at a 6 millimeter shaft and hole relationship here. So if I look down this leftmost column, this is the basic size here. So these are millimeters. So I'm looking for one that my millimeter fits in. So this particular row is 5 millimeter max. It doesn't really have a listed min. It's kind of interesting, but here's a 6 millimeter max. So here's an 8 millimeter max. So I'm going to go to this 6 millimeter max row, and then I'm going to look across this. And then what I'm looking for, this is kind of a weird backwards way of searching this, but it's like I'm given this information, maybe from engineering or something, and and maybe it's my job to classify this kind of fit. Maybe we or could be the other way generally, is that we know what kind of fit we need, and then we'll probably have to look for those dimensions. So this kind of problem is a little bit backwards in my mind, that I'm actually given the dimensional constraints of the shaft and hole, and I'm going to look for what kind of fit that is. I mean, it could be, I could do either way. Like, it depends on which way I'm researching, maybe what information I have. I could see it either way, but maybe it's more common to be like, hey, we know what kind of fit our part's going to have. Go ahead and figure out what the part shaft and hole size would be for that fit. So I feel like that's a more common approach to this. So this is a little bit backwards, but could be done. So what I'm saying is I already know that these are my dimensions of my shaft and hole. 6 to 603, 597 to 594. What I'm going to do is go across in my call in my once I've determined my row that I live in with my basic size. I'm gonna look across here for some dimensions that match my shaft and hole combination. So I'll just look for the whole like I'm looking for the numbers on the whole columns for these different fits uh, that are 6 to 603. And um, all I want is to pull out my highlighter for a second once I get it. Great, highlight. So what I'm doing is I'm coming across here. I'm looking for a hole size that's 6 to 603. It's not that. That's not my dimensions. Hey, there's a 6 to a 603. Yeah, this is it. This has my dimensions for sure for my hole. I'm just going to check the shaft column and see if it matches my actual shaft here. 5.97 to 5.94. So I've got 603, 597, 594. So both the hole and the shaft, this matches what's in my problem to look for. So I'm liking this. I'm liking this as a free running a hole and shaft that matches mine. What you'll find is if you looked at any of the other metric charts, this relationship probably doesn't. These dimensions are probably not in any other kind of fit. So if I look over here, nope, those aren't the same. Those aren't the same. Those aren't the same. Even if you were down, even if you'd missed this the first time around, and you go down to the next chart on a 6 millimeter basic size, I don't think we end up coming up with that the dimensional constraints of our shaft and hole. So that one, see, it doesn't show up there. It's not going to show up here either, from what I understand. Nope. But I'm just looking at the hole sizes and they still don't show up. So there's really only one row that matches our particular problem here. So that is our fit for sure, based off our size, based off our tolerance size, really. So here it is. So pushes me into this column, free running. So we've been able to say, yeah, they put clearance here. I mean, these are clearance fits. They're not like an interference or if you just write free running, that's fine. It's free running, and then I want this code. This is the most useful stuff for me in doing these assignments, right? Is that I'm starting to look and kind of make sense out of these what this code means, so that when I run a computer program where these codes are automatically loaded and I see these, I'll be like, hey, those are metric based hole and shaft basis like clearances. I remember seeing them in school or something. If I see an H9/D9, maybe that thought process would trigger in my brain because that's all and that would be a goal for me here is that we're starting to recognize some tolerance codes for metric and standard. RC 1 through 9, LC, LN, FN type fits, and then we have these other metric type codes. Yeah. So you'll see this in Inventor. Inventor, and I'm sure SolidWorks, I'm even sure Creo maybe even has I'm gonna start saying Creo a lot now too, since they brought that up. And if you're ever looking for that, hey, I'd encourage you. You could look up on YouTube, and I'm sure there's some Creo training on there. Just remember, it's like you could look for PTC wind chill. That's the yeah, like the site uses Creo more than just MFC. Other like NRF mechanical drafters also use Creo for their drafting purposes. And um, but it's like a PTC Windchill is the company that makes Creo, and they make a bunch of other programs too. So yeah, do some YouTube university studies on. You'll see people driving Creo, and it probably just looks a little different.
I was just like how name it looked into like really.
Oh yeah, you already looked it up. Yeah, yeah, cool. See, you're already doing research. That's what we want. Somebody that, yes,
I'm sure
jump
there's
in.
a lot of just like glancing at it, like how that's.
It's kind of same. Let's probably get similar to a 3D like modeling format. Yeah, yeah. I have heard it's a little bit like people that knew my I worked with some people that were ISU students, and they were mechanical drafters at NRF, and they were using Creo. And I asked them about it. I'm like, oh, and I knew that it was weird. He was an ISU drafter student. He's been out maybe 7 or 8 years. I actually, and then we worked at common companies before he went to NRF. He worked for the company that I worked for as a drafter. We never worked there together, but that was with my food processing, Idaho Steel Products was where I spent a lot of time drafting. And he had also worked there right at not too long out of school. And so he knew Inventor really well. He had ran Inventor at Idaho Steel Products. And so when I met him out at NRF, I was like, "Oh, hey, how do you like Creo compared to, Inventor?" He's like, "Oh, it's horrible to get used to." Like Inventor, I think is a better streamlined program, a little more user friendly to use. He told me that Creo was a little bit more manual. He's like, it almost has like it's 3D, yes, but it's kind of manual like CAD is in some ways. He says it's really like he felt like it was like way more button inputs to get commands done than it is in Inventor. And so he just felt like it's just a learning curve and it's clumsy. Then he's like, then you get used to it after running it for a while. But it's he said he felt SolidWorks and Inventor were more intuitive maybe. So that was I just remember him saying that. And then I had access to run it, but it wasn't I was a facilities drafter for NRF, so I was in Revit and CAD, and so I could have played with Creo, I just never found time to do it. Revit was keeping me busy enough, but anyway, side note there. But what we've got is this column. So I'm a free running fit. So I'd say free running, and then I have this code that would be an H9/D9. And then once I've determined that this is kind of the classification of fit, how I would know that it's a whole system is because our chart is a whole basis clearance fit. So there's two charts of whole basis type fits in this appendix, and then there's two charts of shaft basis type fits. So it just means that this particular, this relationship of this hole in this shaft are free running. They're a clearance type fit, and they're based off the hole, is what I would say. They're a whole basis type of fit. And then the last thing you would need to know is the IT grade. And that I think that is said here that it is just the IT grade is the number with the classification here. So it's the nines on these. H9 and D9. The 9 is the index. And what the index is, I don't, or is it, wait, they call it the IT grade, sorry. The IT numbers are a set of tolerances that vary according to basic size, provide the same relative level of accuracy. The number in the fit specification represents the IT number, the small. And so, yeah, 9 is the IT number that would come out of that H9, D9 classification. They're not always the same. I mean, that happens to be the way they're designated in this fit. If you'll notice the next one over, it's an H8, F7 fit. So it's essentially the IT numbers would be 8 for the hole and 7 for the shaft if you ended up in this column. So that's the way this chart works. And this is the way mechanical drafting works sometimes when you're doing a research project. You end up researching through a lot of data sheets as a mechanical drafter for sure. Sometimes you're pulling the data sheets off of like equipment online and just trying to search through it, making sure like where I would use this, maybe if I thought of a situation where I would use something, is that if I'm designing an auger, like let's say I'm going to pull up Inventor just real quick, just because I have an auger that's in here and I haven't sized a bearing for it yet. So this is a project we'll work on next. Let's see here. Screw conveyor right here. I think this is the one. If it'll open, if it still finds the link to my drive, that'd be great. Looks like it will. So what I got to do on this thing here, this is an auger. It's in a housing. This thing spins around. I haven't finished the shaft. I haven't finished the shaft stuff yet here. I've got a piece of pipe in there holding my auger here, but eventually I'm going to have a shaft that's going to come out through this end plate here. And then I've got this little hole pattern right here that I'm going to slip a bearing on that's going to hold that shaft in place and allow it to spin. And one end is going to be one end that has, oh, I've already started working on this shaft. So this one already hooks to the auger here. And so this one is ready for me to slide a bearing over the top of this shaft. and then to bolt it to this end plate so that this auger will be suspended in this housing, and then I'll put a this is a long shaft, so I can hook a drive motor up to it and put some power on this thing, and then and let it spin. And then whatever I dump in the top of this hopper here, uh, this thing will be spinning and it will auger that material down and out through this here. So this will be an inlet here and a discharge here. But what I need to finish here, which is my project over for my Christmas break here, is I gotta go find some bearings to slide on this thing. And bearings are just gonna be kind of like a hole. They have a hole to go over this shaft. And they're going to be a part that I'm going to buy from a supplier. I'm not going to build my bearings. I'm going to buy them from someone that builds bearings all the time. And what they're going to give me is they're going to give me a data sheet for my bearing, and they're going to say, "Hey, here's I need to know what my basic size of my shaft is." So I need to know essentially what this diameter is, and the thing that's driving this diameter is really the size of my auger and everything. Like so, the size of my housing and how big this thing is what there's sheets that I checked out to say, oh, that's how big this shaft needs to be because that's an engineered design that's going on here. In order for this not to break and crack in half on me, if it's too big or too small, if it's too big, this thing could break on me. The actual auger as it moves the material could break something inside that if this shaft is too big. And if it's too small, maybe whatever I'm trying to auger through here will have too much torque or too much resistance and it'll break my shaft. So this had to be an engineered size. And then once I knew that, which I actually found with some research and some data sheets to find out what's because the engineering for augers and screw conveyors has been done long before us, and we just have reference data to look through. And then once I've sized my shaft for how big this auger is, then I'm going to go and find a bearing that's going to slip on it. And then the bearing is going to come with a bunch of data sheets that says, hey, here's how big you need to make your shaft to fit our bearing accurately. And I have to know that. And then I can apply the tolerance to the shaft for my machinist and say, hey, I'm putting this bearing on it. Its data sheet said I needed to be under this kind of fit type or its tolerance. And then my machinist would need to know that to be able to turn this shaft down to fit my bearing. And so that is the kind of work that a mechanical drafter will have to research work that's just a part of your regular everyday life. The engineer is going to sit there and crunch everything for you. They're going to say, hey, just, in our library, we have like the screw conveyor, sizing sheets. Go ahead and dig through that, enjoy. So you'll sit there and look at that for hours and then start designing behind it. And then we'll decide, well, which bearings do we want to buy? And there's about 1 million manufacturers of bearings. So you've got to know what your company likes to use. And then you're going to go to the data sheets that are always found online. They'll even have models of their bearings, 3D models of their bearings. I can just bring in and slap on this thing. So I don't even have to model their bearing. I just need to know which manufacturer bearing we're going to use, pick the correct size, get its data sheets, which comes usually as PDFs, and then steal their model. Usually manufacturing companies, as a drafter, you can work for those kind of companies and do the 3D modeling for their designs. And they put them on their websites for people to pull and use in their modeling process. And I'll do that same thing for the actual drive and gearbox on this thing. So what I just wanted to explain is the kind of research I'm doing on these kind of data. I view this appendix as kind of a data sheet. And this is just part of this is mechanical drafting 101 for sure. Yeah. Oh no. Good. Yeah. Yeah, I think they always use lowercase ones for the shaft. I think it's like a quick indicator. I'll pull back up my data sheets that I think the large capital letter is for hole designation, and then the smaller one is shaft. So it's one. I think it's an indicator if when you know those kinds of codes that
The hole is larger than the shaft.
I guess so, right? And so it's got the capital letter. And it could be that it's like this is a whole basis. So let me look. I just want to double check myself that maybe it's capitalized because it's whole basis and that's the preference. But let me look at one that's shaft basis. I think it still maintains that relationship. If you see a capital, that's the whole designation. This lowercase is shaft designation. And I think it's just that the metric system whenever they decided to have a shorthand classification of fit code. That's how they coded it. Yeah. You'll see that's common in all these columns. Yep. That's a good question, though. So, hey, Chris, what is it? Oh, I don't know. Oh, USB to USB. And I have it. It actually is in the chart. It is captured. Yeah, so what I'll do is these are the ones you need to do, B, C, and D. I think we've determined, I think I'm recording again. Yeah, I am. I think we've determined that you won't be able to come up with an IT grade system and fit for B because it's not if you're looking for this size in this chart, you won't find it. You can do all the work ahead of that. You can do all of the, give everything until all the deviation stuff and size and tolerance. You can figure that all out. You just won't be able to finish that out. And that matches my notes from last year that I have it as not an appendix. We would need a different appendix. It probably does exist, my guess is, or maybe it doesn't, but yeah. And then was there some other questions on C? I don't know. I have all the information on mine. On C, I have it as a locational interference, is what I ended up with. So for the fit. And then on D, I have it as a force. So on my assignment sheet, it looks like I was able to figure out which ones they are. But I'll leave that to you guys. I'm going to jump into number 4, whether or not you guys are ready or not. I'm doing it. So here we go. So I'll pick a new color with my highlighter because I'll go highlight something else here. But I don't have my worksheet 4 open yet, so I'll open that up real quick. It looks a little bit more like worksheet number 2. So I'll push it over here. Worksheet 4. So I'll look at the example here for A and fit 1. It looks like is all the example was. So these problems look like this. We're looking for a basic size. Basic size is just given to us, so that's easy. 5. 5 is our basic size. For both, they're not separated hole and shaft so much here. And then we're just given the actual fit. So for fit 1, all we have to do is write in it's an H11, C11. So I'm going to go to the chart and find this, and then it's just a matter of finishing off what those limits are. So it's kind of this is the way I would normally think you'd probably use this is that you kind of knew what kind of class of fit you were looking for, and then it was a matter of going to the chart to find what the tolerance is. So that this worksheet's driven more like I would think of using this information that you knew what kind of fit you were trying to design around, and you just wouldn't know what the tolerance of that fit is without a chart. So this one we've determined, okay, engineering's determined we need an H11, C11 fit. And I'm like, okay, I'll go to our appendix. I don't know what that is, but I know I've got 4 charts to find it. So I'm just looking for H11, C11. I don't see it on H11, C11. Oh, it's the very first sheet that we have is an H11, C11 hole shaft uh, type of fit. So then for the whole, all I have to do is pull out those. It's the basic size is 5, so I'm going to go to the 5 max row, and so this should be the data that I need to pull into my worksheet here. So they should have 5075, 5075 to 5. It wouldn't matter which one you put in which year. You may have to worry about it if you're doing your subtraction problems to find out tolerance or whatever. But in these questions, we don't have to. All we need to identify is the pretty much the min and the max size here, or the LMC, MMC. That's what we should call it, LMC, MMC. So what we got, 493 and 4855, 493, 4855. Yeah. So these ones I feel like are quite simple, maybe. I haven't pulled up my answer sheet to see if any of these, I have all the answers for these, so they must have been able to match the match. So this one's really, yeah, that's all we need to talk about on this one. Worksheet 3 might be the hardest one, but worksheet 4 is pretty easy. And it looks like we're going to finish A column fit 2. And then we got to do B column fit 1 and 2, C column fit 1 and 2, D column fit 1 and 2, and E column fit 1. So we should have a place to put all that up. Fit 1, fit 2. Oh, that's why these are a little bit bigger, because I can put both fits under the same table, I think. Yeah. Excellent. And then for E, we only need one fit, so it's just a smaller fit or column here. Good. that all fits on one page. That's it, you guys. That's the tolerancing worksheets. It'll be, I think it'll be a couple weeks before there might be a drawing we do next week where we actually do like apply some of the tolerance and look at the dimension styles that exist in our template already. So and then to maybe apply them. So yeah, I think it shows up. It's just we don't widely use it yet, like actually tolerancing our prints. We just kind of plant the seed now and we'll get there. I can't remember when we start. It seems like we end up doing a few drawings where we have our dimensions as tolerances. So stay tuned. It's just not this week. I can't say we have to come back to this. I think we come back to this appendix a little bit more. I just can't remember. Anyway, it must be on a drawing maybe. But okay. So I'm going to put that one over. That is the end of that one.